All right. Hopefully that is showing to everybody. So since this is going to be very much a follow-up on Joe's talk, but I do have a graph of some of the poles of one of the Aguza zeta functions that Joe talks about, at least for a particular n equals 20. You know, it's a geometric picture. We do know something about the real parts of where the poles could possibly be. You always have the issue that, you know, Joe kind of alluded to, that there could be cancellation, right? So you don't necessarily know that a pole is there, but you know kind of where they can't be, right? You know the real parts of where the poles can be. And we know kind of a lot about the multiplicity of the poles. You'll see that in the example, at least that I compute, as you get farther away from the line real part of S equals -2 over n, right, that critical line, the poles become more multiple, right, become kind of a higher multiplicity up to a point. So at any rate, it's a picture which maybe is illuminating, maybe not. So. Oh yeah, we're on my my iPad, so you're going to get little email messages from time to time from all of my students saying why, and I can't figure out how to not get them to show up on. So, but I mean, the nice thing about doing it this way is I think I can write on it. Yes. So, thanks to the organizers. I can only imagine that this was even harder to organize a conference during COVID with everybody all over the world in different time zones than it would be just to get them all in your city and all in the same room at approximately the same time. It's probably a little bit easier.
So we have 2 minutes before the next talk. Let me tell you something, Joe. Are you familiar with the notion of topological zeta functions?
Yes, I actually threw in the limit as p goes to 1 for you.
Yes, but let me tell you something. You computed that limit. The limit that you computed is not the topological zeta function. It's just a part.
Ah, okay.
Because in the calculation you use a formula that is valid only in a certain part of the complex plane. Mm-hmm. If I understood correctly, you computed a part of a topological zeta function. In general, it is known that this is a rational function. You see, but this is important. This is important.
My talk will likely go a little fast because Joe has already laid the groundwork, as it were. So. All right. Well, again, thank you to the organizers for this wonderful conference. I am the next speaker, and I will be speaking on p-Adic and random p-Adic electrostatics. So kind of focusing on some of the things that you've already seen. Let's see if we can't make this work. All right, my notation is going to be slightly different. You saw some of the notation that Joe used. But so K is going to be a local field with a non-Archimedean absolute value. If you want, you can think of this as being QP with the regular p-Adic absolute value the entire time. The set of things with absolute value less than or equal to 1 is the ring of integers. I use O for that because number theory. You can think of that as being ZP, right, the p-Adic integers, or just the closed unit ball in QP. There is also the open unit ball. This is identified with a unique maximal ideal. So has a little bit of algebra there, but the open unit ball I use M for. And then the quotient group is congruent to the finite field with Q elements. But generally, if you're in the situation where you're thinking of K as being QP, then the situation you're in right here is Q is just going to equal a prime. More generally, it's going to be a prime power. There's certainly no problem with prime powers. And as a matter of fact, we will see before too long, we will move some of this calculation off of the primes completely. It will turn out to be slightly useful a little bit later that you can always write that maximal ideal as a principal ideal. So you can find an element pi, which generates that maximal ideal. In the situation where you're in QP, then pi is just equal to p, the prime itself. And we will normalize our absolute value so that the absolute value of the uniformizer is equal to 1 over q. This is just all standard. A little bit more setup, and then we'll get back to some fun pictures. I'm going to use script B to be the Borel sigma algebra on K, so basically the one generated by the topology. I'm going to use mu for the same Haar measure that Joe used, so normalized so that the measure on the integers equals 1. Some nice properties of a Haar measure is, well, first of all, it is translation invariant. So mu of alpha plus a neighborhood B is just equal to mu of B, right? That's the translation invariance. But it turns out that Haar measure also plays relatively nice with respect to dilation of neighborhoods as well. And so when you multiply a neighborhood by an element, the measure changes by the absolute value of that element. Okay. So let's just look at a picture of what I mean. The situation where Q equals 5, this is just the situation where you're looking at Z5. In the gray shaded area is the maximal ideal 5Z5. I like to think of the p-Adics as kind of having this fractal structure. You should, if you want to think about them geometrically like this, you should identify the p-Adics with the fractal boundary of this region, right? So that's a little bit hard to discern. Yeah, so let's just zoom in a little bit on the structure here. If you look at the maximal ideal, if you pick any element in the maximal ideal that is not in the square of the maximal ideal, right? So any element that's an m but not an m squared, then that will be a uniformizer. You can pick your favorite element there and it will generate that maximal ideal. Again, you can always take that to equal p if you're just working in QP, ZP, and PZP. All right. So initially, let's just look at 100 IID points chosen uniformly with respect to mu, right? So just basically throwing a dart at the, in this case, the 5 Adics 100 times, and you get a picture like this, right? But as Joe talked about, the question is what if these points are electrons or, charged particles that repel in some sense? And what you expect is a different sort of picture. So let's just compare these two pictures. This is one where the charged particles, right? And here's one where I chose things just IID, and you'll see places like this, right? In the IID situation where particles can be very close together. And they're not just very close together, they're very close together in the p-Adic metric, right? It is possible to draw 2 points that are relatively close together in the ordinary metric, but that are not actually close together in the p-Adic metric, right? So for instance, here, if I put, oh, shoot. No, let me make that play again. If I were to pick a point right there and a point right there, those points would look very close together, right? But they're actually far apart in the p-Adic metric. Right. At any rate, so the setup is just as Joe set us up. If I take x1 and x2 to be the location of 2 charged particles, in this case, I'm assuming that the charges on the particles are the same. then the energy of the system is going to be given by the negative log of the p-Adic absolute distance between the particles. So if I have a number of different particles, so if I have n particles at the x1 through x capital N, then the energy of the system is just the sum of the pairwise energies. So I sum over all pairs of particles. I look at the log of the p-Adic distance between those two things, sum that up, put in a negative sign just to make sure that the sign convention works. And this is the energy of the system. Right. I'm going to assume here that all of my particles are locked into a compact region. So in general, that's going just to be the ring of integers. It's a natural place. So I don't have to introduce some sort of external field like Joe did. He had this row function that essentially made sure that the particles didn't all eventually run to infinity. I'm just going to put them in a box, as it were. Right? Just put them. And then the probability density of finding the system in a particular state when the temperature is held constant. So again, I'm using this beta to be 1 over the temperature before. Well, the probability density is e to the minus beta, the inverse temperature parameter, times the energy. And as Joe indicated, this basically disfavors high energy states, and it disfavors high energy states more the lower the temperature is, right? So the idea is that if the temperature is high, there's more thermal energy available for the system to put itself in a more elevated state versus if you're at a very cold temperature. So this is just the Boltzmann statistics. All right. So when we do this, right, when you actually do the exponentiation, what you find is that you get a product of differences of those roots with absolute values. This is, of course, where my research came into the game initially, because I was once upon a time very interested in integrals like the classical meta integral, where you had Archimedean integrals where a van der Monde determinant appeared somewhere in the integrand, right? That like a Selberg integral or the classical meta integral. So that was kind of my initial foray into this field. And then because I was raised in number theory, the idea of doing it p-Adically seemed natural as well. All right, again, the z, I use slightly different notation, but z in beta is going to be the canonical partition function. So the integral of the absolute van der Monde determinant to the beta over the n-fold copy of the ring of integers. This is exactly the simplified version that Joe showed you that did most of the calculations with earlier. So this can be expressed as a sum over splitting sequences of certain rational functions that you saw. Okay. This is an Agusa local zeta function for the van der Monde determinant, with the Schwarz-Bruhat function just being the indicator on ON. So it has kind of a classical life in terms of Agusa zeta functions. And more generally, it is useful to look at what happens if instead of integrating over just ON, we integrate over some other Borel set to the N. So the n-fold copy of some other Borel set. In general, kind of like what Joe did before, that the other obvious Borel set to one might care about integrating over would be the maximal ideal. And then coming up with some sort of relationship between the integral over the ring of integers to the N and the integral over the maximal ideal to the N. Okay, so that will come up. And then the probability of finding all of your particles in a particular set B is given by, well, you compute this integral Zn of capital B, right? So you integrate over Bn, and then you divide by the partition function. So having some sort of expression for that is useful just for straight up computing the probabilities. And also, as Joe noted, various expectations with respect to beta give you various kind of macroscopic properties of the gas. So there's lots of reasons to study these partition functions. Okay, I want to do one little thing. I think of this as kind of a push down operator. It's what happens if you take a set in ZP. So just take your favorite ball in ZP and multiply it by P, right? Or multiply it by the uniformizer. It's just going to kind of push that set down by one level, right? So in particular, what I want to do here is note that, well, if I look at the partition function, when I integrate over a pushed down set, right? So I'm basically just taking the set and multiplying it by pi. There's a relationship there with the partition function for the unpushed down set, right? So basically the fact that this is an Agusa zeta function with the polynomial inside the absolute value being homogeneous actually allows you to quite easily come up with a relationship between the partition function when you integrate over, say, ZP, and the partition function when you integrate over, say, PZP. There is a relationship between those two things, essentially just because the polynomial and the integrand is homogeneous. That gives you the n choose 2. And these are exactly the n choose 2s that showed up in Joe's calculation as well.
I should actually add to this. This is exactly what you need to pull the row function out. That was like the first step. Yeah, so this trick is important.
All right. All right. And then I'm just going to abbreviate things in the situation where the classic partition function, the one I care about most, is when we integrate over the ring of integers. I'm just going to use z in for that. And then z bar is then going to be what happens when we integrate over the maximal ideal. Those are the two most important, just as Joe showed you before, because I'm going to show you kind of the p-power law again, because I want to generalize it. Okay. So moving to the grand canonical ensemble, this is the situation where we go from fixing the number of particles to allowing the number of particles to vary in a very specific way. So what we imagine is that each particle in our system costs us some fixed amount of money, right? So I'm borrowing particles from a big particle bath. I'm also borrowing energy from that heat bath. But the cost per particle is what I'm calling chi. Sometimes that's called the chemical potential, right? And then when you set up the energy then is the cost per particle minus the log of the absolute values of the distances between the particles. The probability density of finding the system in state X when the temperature has held constant then is given as follows, right? I do have to throw that in factorial in the denominator now because all particles are indistinguishable, so that becomes important, right? But now the partition function has to be, essentially it is an integral over all possible states. And so the states can be broken up in terms of the number of particles in the system. And so the partition function becomes a sum over, well, pieces, which correspond to number of particles in the system. And each one of those corresponds, or at least has in the summand, the partition function for the canonical ensemble. This is all very classic stuff. So feel free to stop if you have questions about anything, though. Okay. All right. So at the end of the day, what we get is that the grand canonical partition function, here I'm still writing it in terms of the chemical potential. I'm about to do a substitution to get rid of it. But you can see right here that it is essentially just a generating function of the canonical partition functions. And we're going to make that more explicit, as Joe did before. It is traditional to introduce something called the fugacity, which is e to the minus beta times the chemical potential. And when you do this, you see that literally the grand canonical partition function is the generating function for the canonical partition functions. I apologize for going through all this again. Joe already did all of this, but I'm going to generalize it here in a second. So it's useful to kind of see how some of the parts kind of decompose. Okay, so it's a generating function. Here's kind of the central observation, and it's the same observation that Joe gave you before, is that if I take two particles and that they are in different cosets of the maximal ideal, then the log of the distance between them is 0, right? That is, two particles that are in different cosets have 0 energy of interaction, right? They cannot tell. If you're in the 1 plus m, you do not know what's going on in m, right? There's no energy of interaction there, which basically allows you to break up the system into p, if you have p cosets, into p different identical systems. So let's just do that. So all I'm going to do here, right, I'm going to read my email, is I'm going to just reorder. I can take the vector, which gives me the locations of all the particles. I can always permute those in any way I want, right? Permuting them is not going to change the physical system. So I'm just going to organize those so that I take the first however many particles that are in the maximal ideal. I'm going to represent that as x to the 0. And then I'm going to look at the next however many particles are in 1 plus the maximal ideal. That's the vector x to the 1, et cetera, et cetera. And if I have q total cosets, right, then I'm basically just going to break up my state into which coset of the maximal ideal they fall in. But then when you do that, this doesn't necessarily look like it makes life easier. But the energy, it becomes clear that the energy of the system is just the sum of the energies of the systems in each individual coset individually. We call this the additivity of energy over cosets, right? This is basically the main observation we make, right? Not a particularly hard observation, but it allows for some really nice uses of Fubini's theorem down the line. All right, so the theorem that Joe showed you, this is in slightly different notation, is if you want the partition function, so the integral of the van der Moen determinant, absolute to the beta, over the ring of integers, you can replace that with, take the same integral, but integrate over the maximal ideal and raise that to the qth power. So this is the q power law or the p power law, depending on the number of cosets that you have. So if we look at this more explicitly, right, I mean, and the theorem and as it was expressed before is much prettier, but let's just break it out, right? It means this, right? This is literally writing down the two series, the series on the left and on the right, right? And you can do that integral on the right-hand side. Notice the integral on the right-hand side, right, is an integral over the maximal ideal. But we said that there is a relationship between the integral over the maximal ideal and the integral over the entire space. And that introduced these terms right here, q to the minus beta n choose 2 and q to the minus n, which in this case I have chosen to attach right there, right? And so now what I have is a relationship where I have a power series with coefficients on both sides that involve the same integral, right? So now I should be able to come up with some sort of recursion, which will allow me to somehow solve for that integral. Okay. So there are a couple easy cases to check, right? We should make sure that this jives with our intuition. In the beta equals 0 case, when beta equals 0, that's like being at infinite temperature, right? And when beta equals 0, if you're at infinite temperature, there's no correlation between the particles. In that case, the partition function becomes purely exponential, which you kind of expect. It's kind of a Poisson process at that point. And you can see that the exponential does indeed satisfy e to the t equals e to the t over q to the q, right? The other easy case is when beta goes to plus infinity. This situation right here corresponds to absolute 0. When you're in absolute 0, you can only have particles in the absolute ground state. And as soon as you have two particles in the same coset, you can't be in the ground state anymore. So when you're at absolute zero and you have a fluctuating number of particles, it's actually going to tell you you can have at most one particle in each coset. And what you essentially find is that the partition function, the integral over the maximal ideal becomes 1 plus t. And then the partition function, when you integrate over the entire ring of integers, is 1 plus t over q to the q. So it satisfies the q power law here as well. So you can at least verify in these two easy cases that indeed you satisfy the q power law, but it's true in general. I should say there's one other interesting case, and that's the case when beta equals 1. When beta equals 1, you just get a power series in T, right? There's no, you essentially evaluated that away. And this is just the generating function for the probability that a degree n polynomial with coefficients, with integer coefficients, splits completely in the local integers. Right? So there's actually a kind of another interesting interpolating value of beta equals 1. And as a matter of fact, that value of beta equals 1, that interpretation right there is very much in line with some of the beta equal 1 interpretation of Archimedean versions of these sorts of integrals. That comes from a Jacobian calculation. When you move from, when you do the Jacobian from the change of variables from roots to coefficients, right, you get a van der Moen determinant to just the regular absolute value to the first power. And so you kind of see a similar result appearing. At any rate, neither here nor there. All right. So this provides two different recursions for Zn. One is kind of an exponential recursion, but the one that Joe talked about, which is more interesting, is the quadratic recurrence. He wrote it in a slightly different way with hyperbolic sines or hyperbolic cosines, but by and large, the trick is the same. It's finding some sort of quadratic recurrence for z so that you can solve for z capital N in terms of z little n for all lower n. And this is relatively quick to do. So for instance, if we look at z20 of beta, right? So this is looking in the complex plane. Everything is backwards just for stupid reasons, but we see the y-axis. Everywhere in gray is the function is holomorphic. So it's holomorphic to the right of real part of s equals minus 2 over n. And then you can see kind of where the poles line up here. I tried to make the higher order poles have more circles. So if you have keen eyesight, you could count the multiplicity of each one of those poles. But you see that the poles that are very close to the line of analyticity are single poles. And as you kind of march away, you get poles of higher order. This thing is periodic with period, I don't know, like log p or something in the there is a periodicity. Yeah, so you can see all these things right here. It's a very complicated rational function, even for say n equals 20. All right, I want to write one particular corollary here, because this will come up a little bit later. It's just an analog of the p power law or the q power law, as it were. And all I'm going to do here is I'm going to say if I'm given a formal power series f, okay, so it just has these coefficients a, n, then I'm going to define this f bar to be, well, almost the same coefficients. I'm going to take the an's, but I'm going to multiply by that q to the minus beta n choose 2 minus n. That was exactly the term that kind of popped out of the integral when I pushed down the domain, right? So if I have an f and an f bar, and then I can define an operator on the set of formal power series just by taking f bar to the q, right? That will just, and you give me a power series, I can make a new power series in this way, right? Well, then it turns out that the partition function that we've been talking about is a fixed point of that operator, right? So AQ of the partition function equals the partition function. Here, because this operator is acting on formal power series, the partition functions that I'm putting in there are grand canonical partition functions. Those are the ones that are power series. And so we're going to be generalizing kind of this notion to other topological spaces and relating them to the partition function studied here. So I need to introduce just one more thing. I need to make the partition functions that I've been talking about explicitly depend on Q, the number of cosets of the maximal ideal. Right? So I'm going to now call those same partition functions ZQ. We haven't had to do that before because we've been dealing with one Q at a time. Okay. One thing I should say is the ZQs still make sense for any integer Q. As a matter of fact, you probably want any integer Q bigger than 1. But for any integer Q, and the reason basically is you might complain and say, well, there's no such thing as the 6 adics. Well, but there kind of is. They're a group, not a ring, right? But you can still form the Haar measure on it with respect to addition. And so you can form these integrals over kind of the 6 adics or the 9 adics or whatever integer adics you want. They don't have to be prime. It's just the absolute value is no longer an absolute value. Some of the nice algebraic features of those things disappear, but one can still write down the integrals that I've been talking about quite profitably. And I'm going to show you kind of a generalization that will allow you to generalize these sorts of integrals to, well, other profinite completions of other trees. All right. So I should stop right here because I am about to move into a more general arena and ask if there's any questions about what I've done. It's basically been Joe's talk all over again. Okay, seeing none, I'll move on, but feel free to interrupt me at any time. So what I want to do is move to other profinite completions. So here the idea is that the p-Adics, in this case, we're looking at the 5-Adics, are kind of this fractal structure of a tree. And what they are is they are all paths. One way of thinking about a p-Adic number is a path from the center of the tree to the very edge, right? And somehow every turn that you make into one of the cosets at each branch, right, is kind of equivalent to the digits that you would write down in the p-Adic expansion. Not quite, but there's a way to go back and forth between the classic p-Adic expansion written in terms of digits and powers of p and kind of an address on the boundary of this fractal. Right? And basically those digits just tell you the turns that you need to make to get to any point on the boundary. Well, we can do that with other trees. If we do it with the infinite regular 5-nary tree as written here, you will get the 5-Adic integers, but we can do this for other trees as well. So I want to set up that situation. Okay, so the situation I'm going to move to is actually going to be a random tree eventually. So what I want us to think of is let Q be a strictly positive integer valued random variable. Okay, so just a random variable that takes positive integer values. And I'm going to define a branching process with log Q. And what I want to do is come up with a random directed infinite rooted tree T. It will have vertices V, right? I'm going to write, if there is an edge from V to W, right, then I'm going to say that V is a parent of the child W. So I could either say V is the parent of W or W is the child of V. It's useful to have a little bit of notation. So I'm going to write kind of this double bar divides, W double bar divides V if W is a child of V. And if W is just a descendant, I'm going to use a single bar. This is kind of how we use divisibility of prime powers. So For every vertex V in the tree, it has some number of children, QV. And basically the assumption is going to be that each one of these QVs is independent and identically distributed. Right? So basically every parent has the same law for having some number of children. Okay. And then the profinite completion of this is the set of paths down the tree from the root. All right, I'm going to draw a picture here. So this looks like a lot, but if I start here. So I'm imagining now a tree, right? V0 is the center, so it's a node. I want this to be a rooted tree. The arrows are always going to be pointing down, right? And so I see here that the root V0 has 3 children, right? One of those children is labeled A1, right? And then A1 itself has 2 children, right? One of those is labeled A2. A2 has 2 children, et cetera, et cetera. But the rule here is that I want the number of children that each node has to be random, but independent and identically distributed to Q. So basically the rule for the randomness is the same for every node. Okay? And I make an infinite tree in this way, right? I think it's probably helpful, and in all interesting cases, we would have that the expected number of children for any particular adult is finite, right? That keeps the tree from kind of becoming overwhelming. But we get this huge infinite tree. And then the profinite completion of that tree is just the set of paths from the center, from the root to the boundary. Right. All right. We can topologize the profinite completion by saying we're going to define an open set to be all of the paths which pass through a particular vertex. Right? We might call that a neighborhood. And so if I look at the neighborhood V, all of the paths that pass through V, right, that's going to be the neighborhood. So what I kind of think of is, these paths kind of keep going, down, and, there's all of these are like, there's lots of little paths going down. Couldn't draw all the levels, obviously. And I think of the profinite completion as kind of all of these points out here way at the boundary, right? Kind of all of the paths down here. And this part right here corresponds to all of the paths that pass through V. And I'm going to call that an open neighborhood. And then I can make a topology out of that by just topologizing all the sets of open neighborhoods. And it becomes totally disconnected. And you would see that if you had started with a non-random tree that was just regular, right, then you would essentially get just back to the topology on the p-Adics if you had p children for each splitting. All right. It is possible, well, I don't think I need to talk about that. I do want to talk about a measure on this thing right here. So a measure on a random tree like this, or a measure on a tree, is an inheritance scheme. Kind of the canonical probability measure is the one where each child of a parent inherits the same amount of mass, right? So for instance, if we look here at A1, right? Well, A1 was that there's 3 total children of its parent, right? So it gets 1/3 of the mass, right? So all of the stuff that's downstream from A1 gets 1/3 of the mass. All the stuff that is downstream from A2, right? Well, because A2 has one other sibling right there, right? It gets 1/6 of the mass, right? There's 2 siblings right here. So everything downstream from V gets 1/12 of the mass, right? So I can define a measure on my tree by basically looking at how much inheritance would I get. And since tau v generates the topology, it also generates the Borel sigma algebra. And so this gives me a measure on my tree T. I should say that this measure, in the case that if your tree just happened to be, say, the 5-adic, the complete 5-nary tree, this would be the Haar measure on Z5. right? So this is the classic generalization. You could generalize this to other measures with different inheritance schemes. Maybe you wanted the first child always to get more than subsequent children. One could cook something up like that and come up with a very similar system. Seemed right, to be fair. Just how I roll. All right. Okay, well, now that we have a measure, right, from a measure, we can now make a distance function. And we do this by essentially, if I want to know the distance between 2 points, so here I have a point V and a point W, I go and I look at their least common ancestor in the tree, right? In this case, it's V. And I just define the distance between those two things to be the measure of the set of descendants of their least common ancestor. Okay. So in particular, right, if I pick some point over here and some point over here, right, then, you know, kind of following the tree back, I see that those two things right there have a distance 1 from each other, right? And that's essentially if you are a descendant of a child at the first level, right, different children, those are the things that kind of separate. Well, okay, at any rate, again, this distance right here is exactly the p-Adic distance if you had started with the complete p-Nary tree, right? This would give you the p-Adic distance. All right. Okay, so now I have a tree. I have a distance on that tree. I can do electrostatics by essentially making an energy functional by looking at the sum of the logs of the distances between points in the profinite completion of this tree. Minus sign is there for the same convenience as before. We can do electrostatics here as well. So basically set up the Boltzmann factor in the partition function. The canonical partition function here, I'm assuming that I have a fixed number of particles for the time being.
Sorry, Chris, a quick question. The xn are in the boundary of the tree. The variables.
That's right.
Okay, yeah.
You should
so
think
right now this is a random variable. The energy is.
Right now, everything depends on script T, on the random tree that you picked. So this is random, but you could also, at this page, everything on this page you could do for a fixed tree. So if you just picked your favorite tree, you could set up this calculation the same.
Okay, thank you.
Mm-hmm. Okay, and then we can make the grand canonical in the same way, right? So that we did before. We basically look at the generating function for the canonical partition functions. So everything is analogous here. When we do the exponentiation, right, we actually see that this becomes an integral. You know, this should not be it. Well, I should be integrating over Tn. But at any rate, this is an integral of the product of the distances between the particles raised to the beta power, right? Which, if you think about what's happening from the classical case, right? This was the classical p-Adic case. You have the exact same sort of expression. We just wrote that in terms of the p-Adic absolute value because that's how the distance was defined. Okay. I already said that. That's basically if you come from 2 different children, you have distance 1. So we have the same additivity of energy over cosine. The idea here is all the descendants of, if we look at the center, right, if we look at V0, and suppose you have 3 children, V1, V2, V3, any descendant of V2 is going to be distance 1 away from any descendant of V1. Or any descendant of V3 is going to be distance away from any descendant of V1. So things that are different descendants of kind of the first level become independent. And so you would expect that your partition function is going to factor, right, into basically, instead of a product over cosets, it's a product over, well, children in the first generation. Right? So you expect that to come up again, and it does. It's the same additivity of energy over cosets. It's just the random situation. Right. Now, the hope then is that there is some sort of relationship between this partition function here and these partition functions right here, right? These are integrals over the neighborhoods, right? And if there is some sort of relationship between those two things, one hopes, then one may be able to come up with a recurrence for the original thing, right? That is what we did in the case of the p-Adics. We recognized that the p-Adics were formed to be a union of neighborhoods that essentially look identical to the p-Adic integers, right? And that was the thing that allowed us to come up with the recurrence in order to actually solve for the partition functions. Well, our tree is formed randomly, right? So there's probably no structure between what's happening on the entire tree and any subtree, right? The subtrees are just randomly generated. There's no a priori structure, right, between what's happening on the entire tree and any subtree, right? However, if we chose our tree randomly with respect to a branching process, then all of those trees are similar in expectation. Okay, so I think this is the place where right, we had all of the expectations before actually depended on our random tree script t. And for each one of those, I could compute the partition function, right? And so what I'm going to do here is take expectations over all possible random trees. So this expectation is over tau, right? And the reason is because in expectation, all of the subtrees under a child looks the same as the original tree, right? In expectation, not for any particular sampling of that random tree, but in expectation. Okay, and then I can make a mean grand canonical partition function as well, right? At this point, the mean partition function is no longer random. It's just a deterministic function of beta, right? And so I can form the mean grand canonical partition function as before. And our goal would be to find is there some sort of recurrence for this mean grand canonical partition function? Or is there something like the p-power law that would then allow us to find the mean canonical partition functions by doing some sort of quadratic recurrence or some other recurrence? The answer is yes, but I want to phrase it like this first. Okay, so let's just remember the previous theorem or a corollary that I gave for the previous theorem. It said I could make this operator, basically, I'm calling it a sub q now, but a sub q of a formal power series is, well, I take that power series, push it down, and then raise it to the qth power. Right? This was the q power law. And we decided that before that the partition functions for the q-Adics is a fixed point of aq. So aq of zq equals zq. So now what I'm going to do is I have a law for q, right? I know capital Q is a random variable. And what I'm going to do is essentially make a linear combination of those operators from before. In fact, it's going to be a convex linear combination of those operators from before, because the sum of all of these p, the probability that q equals little q, that sums up to 1. Right? So I have these operators, essentially one for every integer q, because remember, I could extend it off of the prime powers, right? And I take a linear combination, a convex linear combination of those operators, and I get a new operator. And then the theorem says that the fixed point of that operator is the expected canonical partition function for the profinite completion of a random branching process given with law Q. Right. There is, I should say that the corollary that I gave before, that the partition functions are fixed points of these operators, is true, but they're also the unique fixed points of the operators where the power series starts 1 plus t plus some other term. That's equivalent to kind of the base case for the recursion or the induction being z0 equals 1, z1 equals 1. That means that the power series always start 1 plus t, and the unique power series, which is the fixed point of this particular operator with that property, is going to be the expected grand canonical partition function. So this is how I kind of think of it. I kind of think of AQ as being a convex linear combination of some other AQs. In this case, if the possible number of children that anybody has is only 2, 3, 4, 5, or 6, right? Then AQ is some convex linear combination of those. And then I think of in my head, I think of, each Z5 as being kind of an eigenvalue of that operator. It's a fixed point of that operator. So in my head, I kind of think of it as an eigenvalue. And so kind of what I think about then is what we have is as AQ varies over this convex linear combination, right, over this polytope, we have an entire family of operators, right, which are given essentially as convex linear combinations of the classic p-power operators. Right, and so you get an entire family of power series. You get an entire family of power series, and those power series are exactly the ones which give you the mean grand canonical partition function, where the Q is determined by that convex linear combination. I don't know if it's a useful way of thinking about it, but there are some really useful corollaries here that I want to write down at least. Just a couple more minutes left. Aha. Okay, so here is one corollary. The mean canonical partition function, right? So this is canonical, right? So you get a function in beta for each capital N, is a rational function in q to the minus beta, which q's the possible number of children at each step. Right. So for instance, suppose that you just did a very easy case where each node, you're either going to have 2 children or 5 children. You're going to roll a die. If it comes up heads, you have 2 children. If it comes up tails, you have 5 children. Right. If you compute the mean canonical partition function in that case, you will get a rational function in 2 to the minus beta and 5 to the minus beta. Right. This suggests to me that there may be kind of a generalization of Agusa's rationality theorem to these random p-Adic local zeta functions, right? So this is hard though, right? Because when you look at an Agusa zeta function, it's classically defined, or the easiest cases are cases where you take the absolute value of a polynomial to a complex power and you integrate over some compact region. That's the simplest example of an Agusa zeta function, right? But on our trees, we don't really have the notion of polynomials. What is a polynomial on a random tree, right? I don't have arithmetic. But there is a suggestion here that basically says that, well, if your polynomial split into linear factors, right, was a linear homogeneous, a product of homogeneous linear factors, like the Vandermonde, or like one of Joe's integrands where he puts the different Sij's on the Vandermondes, right? Those we know how to generalize those integrands, right? I basically would replace every absolute value of a linear factor with the distance on my tree between 2 points. So basically any polynomial, any multivariate polynomial that factors into homogeneous linear factors, I think is going to have this kind of generalized Agusa rationality, right? So that if you did that over the random pro-finite completion of a branching process with law Q, that you would get a rationality result in Q to the minus beta, where Q is all the possible values of children that you would possibly have. So this is, I want to say.
Sorry, Chris, can I ask you something?
Yes.
For a fixed tree, we are really working with an infinite family of trees. We fix one, then the integral, use the distance delta x, y. So that integral is rational.
This, yes. So
No. The last integral in this slide.
This one, right?
No, because okay, no, scroll down, please. When you introduce the generalization.
This one, right? Yes.
The last integral in your slide. Suppose that P is a fixed tree, and the distance is the simplest one, delta, the distance in the tree. You know that this integral is rational?
No.
Yeah, you know only that that the expected, this is really a random variable.
Exactly.
So
I don't expect that for maybe for special trees, right? If your tree has structure, the thing that we really have used before, both in Joe's integral and these, is that you have this kind of just self-similar structure. So, and in expectation with these random trees, in expectation you have self-similar structures, right? Because all of the trees from any child are going to look the same. But for any particular random tree, they don't. So, but what we need to do in order to formulate what the Agusa rationality conjecture would be is I still need to figure out for those random trees, what is the analog of the absolute value of a polynomial, right? Because what I want to do is formulate the notion for a random tree, what an Agusa zeta function is, and then show that when I take expectation over all of these branching process trees, that you actually get a rationality result, that you get the Q.
I mean, it seems that a polynomial in the deltas is possible. I mean, consider polynomial functions in the deltas of the tree. That's a natural candidate.
I think you're right. I think that is a natural candidate, would be polynomials in the deltas. I think also, kind of moving in the direction of like the Berkovich line, right? Like maybe integrating semi-norms, right? Because the absolute value of x minus alpha is a semi-norm. I think, but let me just move to my ill-formed conjecture, is once we figure out how to define those Agusa zeta functions, right? Once we figure out the right definition, my conjecture is that those are rational functions, which is, of course, the most ridiculous conjecture ever, right? But I think that there is some generalization of what it means to be an Agusa zeta function to these random trees, so that the expected partition functions or these sort of expected integrals actually turn into rational functions. All right, I think, looky there, that's the end.
There is a chance, Chris. There is Muser in the 80s established a result, the following result. She considered a